there is a question that has been quietly ruining the sleep of physicists, astronomers, philosophers, and anyone who has ever stared up at the night sky for long enough to really think about what they were looking at. The question is simple. It is 4 words. And those 4 words, when you genuinely sit with them rather than just bouncing past them, have a way of making the universe feel less like a home and more like a room you woke up alone in without any memory of how you got there. Where is everybody? That is the question. Where is everybody? Where are the signals? Where are the probes? Where are the megastructures and the transmissions and the evidence of all the civilizations that the math says should be out there, scattered across 400 billion star systems in just our galaxy alone, across a universe that is 13.8 billion years old and contains roughly 2 trillion galaxies? Where is everybody? This is the Fermi Paradox, named after the physicist Enrico Fermi, who allegedly asked this question over lunch in 1950, and in doing so, crystallized one of the deepest mysteries in all of science. On one hand, a universe so vast, so old, so filled with stars and planets and the raw chemical ingredients of life, that the existence of other intelligent civilizations seems not just plausible, but statistically almost inevitable. On the other hand, silence. Complete, absolute deafening silence. No signals, no probes, no tourists, no evidence of any kind that anyone else has ever been out there doing anything at any point in the 13.8 billion years this universe has had to produce them. The gap between what we expect and what we observe is so enormous that it has a name: the Great Silence. And there is no shortage of proposed explanations for it. We are going to work through many of them in this video. Maybe life is rarer than we think. Maybe intelligence is rarer still. Maybe civilizations tend to destroy themselves before they can reach the stars. Maybe they are out there, but we haven't been listening long enough, or in the right way, or they are intentionally hiding from us for reasons we cannot fathom. All of those are uncomfortable in their own right. But here is the thing. Here is what most Fermi Paradox discussions miss, gloss over, or treat as a footnote when it should be the headline. Almost every standard treatment of the Fermi Paradox assumes, implicitly, that the question is about space, about the vast distances between stars, the challenge of interstellar travel, the difficulty of communication across light years. It frames the paradox as a spatial problem. The universe is big. Other civilizations are far away. Maybe that's why we don't see them. But the universe is not just big in space. It is old in time, incomprehensibly, almost insultingly old. And when you add time to the Fermi Paradox, when you stop asking, why don't we see anyone out there, and start asking, why don't we see the accumulated evidence of everyone who has ever existed across 13.8 billion years, the paradox does not get easier. It gets darker, considerably, distinctly, uncomfortably darker. Because here is the thing about time. If you factor in even 1 million years, a rounding error in cosmological history, less than 0.01% of the universe's age, a single civilization with anything like our current technological trajectory would have had time to colonize the entire Milky Way. Not could theoretically colonize it. Could have done it. Completely. Multiple times over. And there are 10 billion years of cosmic history during which stars similar to our Sun have existed. Planets similar to Earth have formed, and chemistry similar to ours has had time to run. 10 billion years. If intelligence is even a remotely common outcome of planetary evolution, the galaxy should not just be inhabited, it should be saturated, teeming, restructured, unrecognizable from what we observe, and yet, the silence persists. What the temporal dimension of the Fermi Paradox tells us, what happens to the math when you stop treating this as a snapshot of the present moment and start treating it as an accumulation across deep time, is one of the most unsettling things I've ever tried to get my head around. And by the end of this video, it will have unsettled yours too. That is a promise. Let's start from the beginning. Chapter 1. The Fermi Paradox. What it actually is and why it actually matters. Most people have heard of the Fermi Paradox in roughly the same way they've heard of Schrödinger's cat. They have a vague sense of what it refers to, they can describe the general shape of it, but the full depth of the problem tends to get lost somewhere between the introduction and the first distraction. So before we can talk about what time does to the Fermi Paradox, we need to make sure we genuinely understand the paradox itself, not the summary version, the real version. The universe is 13.8 billion years old. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. Of those stars, roughly 20 to 25% are G-type or K-type stars, stars similar enough to our Sun that they could plausibly host planets in a temperature range suitable for liquid water. That's somewhere between 40 and 100 billion potentially Sun-like stars in our galaxy alone. And we now know, from data collected by the Kepler Space Telescope and other exoplanet surveys, that planets are not rare. Planets are extraordinarily common. Most stars have them. Estimates suggest that the number of rocky, roughly Earth-sized planets in the habitable zones of their stars in the Milky Way is somewhere in the billions, possibly tens of billions. The observable universe contains approximately 2 trillion galaxies, each with its own hundreds of billions of stars. The total number of potentially habitable rocky planets in the observable universe is a number so large that writing it out would take more space than this script. Now add time. The universe is 13.8 billion years old. Complex chemistry capable of producing the building blocks of life has existed since relatively early in cosmic history. The first generation of metal-rich stars, which are needed to produce the heavier elements that biology uses, formed perhaps 10 to 12 billion years ago. Earth-like planets could have been forming, and life could have been originating, for at least 8 to 10 billion years. Our own civilization is roughly 10,000 years old in any meaningful sense, and we have had radio technology for only about 120 years. In the context of 10 billion years of potentially habitable planets, we are brand new. We are the last people to arrive at a party that has been running for almost forever. So, given all of that, the billions of habitable planets, the billions of years of time for life and intelligence to arise, the vast canvas of the universe waiting to be filled, where is everybody? That is the Fermi Paradox. And it is not primarily a question about extraterrestrial life in the casual sense. It is not really about whether there might be microbes on Mars or underwater oceans on Europa. It is specifically about intelligence, about civilizations, about the kind of life that builds things, that communicates, that expands, that leaves marks on the universe that a civilization on the other side of the galaxy could detect without a microscope. The question is why we see absolutely no evidence. Not a signal, not a probe, not a modified star, not an engineered structure, not a trace of any kind, of any other intelligent technological civilization anywhere, ever. The silence is not just statistically unexpected. It is, by any reasonable prior estimate, shocking. It is the cosmological equivalent of waking up in a city of 8 billion people and finding no one else. Not just no one in your house, no one in the city, no garbage on the streets, no lights in the windows, no sounds, no footprints, no evidence that anyone has been here before you in any direction you look. Just empty buildings and absolute silence. That is the Fermi Paradox, and it does not have a comfortable resolution, which is part of why the proposed solutions, which we will get to shortly, tend to be either deeply disturbing or deeply humbling or both simultaneously. Before we move to solutions, let me make one more point about the structure of the paradox that matters for everything that follows. The Fermi Paradox is not simply, we haven't found anyone yet. We haven't been searching very long, and we've only searched a tiny fraction of the sky, with a tiny fraction of possible signal frequencies over a tiny fraction of possible time. That's a valid point. We could be looking in the wrong place, the wrong way, or at the wrong time. But the deeper version of the paradox, the one that is genuinely hard to explain away, is not about our failure to find signals. It is about the absence of what astronomers call astroengineering, physical modifications of the universe at scales large enough to be detectable even to primitive observers like us, across galactic distances. If a civilization had even a few million years of technological head start on us, they would have had time to do things to their star system, their galaxy, or the surrounding universe that we could not miss even with our current instruments. The fact that we see nothing of that kind, anywhere, is the core of the problem. It is not about radio signals. It is about the physical universe looking exactly as it would look if no one had ever done anything to it, anywhere, at any point in the past 13.8 billion years. That is what we have to explain. and adding time makes that problem immensely harder. Chapter 2: The Drake Equation, Putting Numbers to the Silence. In 1961, an astronomer named Frank Drake organised the first serious scientific conference on the search for extraterrestrial intelligence. To structure the discussion, he wrote an equation on a blackboard, not because he thought it could be solved with the information then available, but because it identified all the factors that would need to be known to estimate the number of detectable civilizations in the Milky Way at any given moment. That equation became one of the most famous in the history of science, and it is the formal starting point for any rigorous discussion of the Fermi Paradox. The Drake equation, in its original form, multiplies together the following quantities: the rate at which new stars form in our galaxy, the fraction of those stars that have planetary systems, the average number of planets per solar system that could potentially support life, the fraction of those planets on which life actually appears, the fraction of those life-bearing worlds on which intelligence evolves, the fraction of those intelligent civilizations that develop technology capable of transmitting detectable signals into space, and the average length of time over which such civilizations produce detectable signals. Multiply all those factors together and you get n, the number of communicating civilizations in the Milky Way right now. In 1961, most of these factors were essentially unknown. Today we have made substantial progress on some of them. The star formation rate in the Milky Way is well established, roughly 3 new stars per year. The fraction of stars with planets is now known to be very high, approaching or exceeding 1 for many stellar types, thanks to a decade of exoplanet surveys. The fraction of planetary systems with planets in habitable zones is estimated at somewhere between 10 and 40% for Sun-like and slightly smaller stars. So the first few terms in the Drake equation are not the problem. The universe is clearly, demonstrably awash in potentially habitable real estate. The number of for rent signs on the cosmic landscape is enormous. That much is settled. The uncertainty concentrates in the biological and sociological terms, the fraction of habitable planets where life actually originates, the fraction of life-bearing worlds where intelligence evolves, the fraction of intelligent civilizations that develop technology, and most critically of all, the average lifespan of a technological civilization. This last term, the lifespan term, usually denoted L in the equation, is where the entire calculation pivots, and it is where the temporal dimension of the Fermi Paradox starts to bite hard. Because L is not just a number, it is a statement about whether civilizations tend to destroy themselves or transcend themselves, whether intelligence is, in the cosmic long run, a sustainable phenomenon or a brief and self-terminating one. If the average lifespan of a technological civilization is, say, 200 years, roughly the duration from the invention of radio to some hypothetical self-inflicted catastrophe, then even if intelligent life is reasonably common, the fraction of civilizations active at any given moment would be so small that the galaxy might contain only a handful, and the chances of 2 of them being close enough and active at the same time to communicate would be vanishingly small. If, on the other hand, civilizations typically last for millions or billions of years, either because they solve their existential problems or because they transform into something else entirely, then the galaxy should be full of them, and the Fermi Paradox becomes even more acute than it already is. The Drake equation does not resolve the Fermi Paradox. It sharpens it. It makes precise exactly which unknowns are driving the problem. And the uncomfortable truth is that all the scenarios where n is large, all the scenarios where there are many civilizations out there, make the silence harder to explain, not easier. The more life there is, the louder the silence. There is one more thing the Drake equation doesn't capture in its original formulation that turns out to be enormously important: time. The equation asks about the number of civilizations at a snapshot, right now. It does not ask about the number of civilizations that have ever existed across the full 13.8 billion years of cosmic history. When you modify the equation to account for time, when you ask not just who is there now, but who has ever been there and what traces have they left, the numbers change dramatically and not in a comforting direction. We will come back to this, but first, let us talk about the proposed solutions to the paradox, because understanding them is prerequisite to understanding why time makes all of them harder to accept. Chapter 3: The Great Filter, the most terrifying idea in science. Of all the proposed solutions to the Fermi Paradox, one stands out as simultaneously the most intellectually rigorous and the most emotionally disturbing. It is called the Great Filter, and it was most clearly articulated by the economist Robin Hanson in a 1998 paper that has haunted discussions of the Fermi Paradox ever since. The argument goes like this. We observe that the universe is old, large, full of potentially habitable planets, and full of complex chemistry. We also observe that it appears to contain no other intelligent civilizations, or at least none that have left any detectable trace. These two observations together imply that somewhere on the path from simple matter to spacefaring civilization, there is a step, or possibly multiple steps, that is extraordinarily difficult to traverse. A filter that most combinations of matter and time and chemistry simply fail to pass. A barrier so high, so improbable, so rarely crossed, that it explains why a universe full of potential is observationally indistinguishable from a universe that is empty of anyone. This filter, wherever it sits, has prevented the galaxy from being visibly colonized. It is what stands between a universe that should be teeming and a universe that is silent. Now here is the question that Hansen pointed out is the most important question in the universe, and he was not being dramatic. Is the Great Filter behind us or ahead of us? If the filter is behind us, if the step that is extraordinarily hard is something that has already happened in Earth's history, then we are extraordinarily lucky. We have already passed the filter, we got through the thing that almost always stops everyone, and the road ahead is open. Other civilizations are rare not because they tend to destroy themselves after reaching our level, but because they almost never reached our level in the first place. Perhaps the origin of life is incredibly rare. Perhaps the transition from simple prokaryotic cells to complex eukaryotic cells is almost impossible. That step took 2 billion years on Earth and may have required events of vanishingly low probability. Perhaps the evolution of multicellular life is the barrier, or sexual reproduction, or the development of the kind of brain that supports abstract reasoning and symbolic language. Any of these could be the filter, or it could be some combination of them. If the filter is behind us, then intelligent civilizations are simply rare, perhaps extraordinarily rare, perhaps unique. And the silence is explained by the fact that there is nobody else to make noise. This interpretation, while implying we may be alone or nearly alone in the universe, is actually the good news version of the Great Filter hypothesis. It is humbling and isolating, but it is survivable. We're here. We got through. The path ahead may not require crossing another filter of similar difficulty. The bad news version, the truly terrifying version, is that the filter is ahead of us. If the filter is ahead of us, then the silence of the universe is not explained by the rarity of intelligent life. Intelligent life may be reasonably common, but at some point after reaching our level of development, perhaps slightly after, perhaps well after, civilizations almost universally cease to be detectable. They stop leaving traces. They go silent. And the reason they go silent is not that they hide well or transcend physical existence, or find some ineffable inner peace that makes them disinterested in the material universe. It is that they destroy themselves. Nuclear war, climate catastrophe, engineered pathogens, artificial intelligence that does not share human values and does not care about human survival. Some combination of all of these, or something we haven't thought of yet. A technology, possibly one we are currently developing, that provides the capability for small groups or even individuals to cause civilizational scale destruction, and that essentially every civilization eventually uses to do exactly that. If this is the answer, if the Great Filter lies ahead of us, then the discovery of even simple microbial life on Mars or Europa would be, in the words of philosopher Nick Bostrom, genuinely terrible news, because it would mean that the filter was not in the early stages of biological evolution, and the most likely candidate for it is therefore something that happens to technological civilizations after they reach our stage, something that is, statistically, waiting for us. The Great Filter is already one of the most disturbing frameworks in all of scientific thinking, and then you add time. The temporal dimension of the Great Filter argument does something very specific to it. It does not merely reinforce the two options, filter behind or filter ahead. It introduces a third possibility that is in some ways even stranger, and we will get to it. But first, let's sit with what the age of the universe does to the filter ahead interpretation. If the filter lies ahead of us, if civilizations tend to destroy themselves at roughly our current level of development, then we should expect the following. There should be ruins. Not necessarily the kind of ruins you could see from a planet's surface, but astrophysical ruins, civilizations that destroyed themselves 500 million years ago on planets that were otherwise similar to Earth should have left detectable modifications of their planetary atmospheres. They should have released detectable waste heat signatures during their industrial phases. If they built any kind of large structures before their end, those structures might still be detectable. The universe has had billions of years to accumulate the ashes and remnants and final broadcasts of all the civilizations that made it to the stage we are currently at, and then failed to pass the filter. We see none of that either. The galaxy is not just quiet, it shows no signs of past activity, no signs of civilizations that existed, thrived briefly and ended, no astrophysical artifacts, no modified star spectra, no megastructure remnants, no anomalous atmospheric signatures on the thousands of exoplanets we have now characterized with telescopes. Just a pristine, untouched, undisturbed galaxy that looks exactly as it would look if nothing had ever happened in it. That is the temporal version of the filter problem, and it is what we are building toward. But we are not ready for it yet. First, let's talk about the full menu of proposed solutions to the Fermi Paradox, because we need to understand all of them before we can understand how time systematically destroys most of them. There are many proposed solutions to the Fermi Paradox, and they can be roughly sorted into three categories. Solutions that say life is rare, solutions that say intelligence is rare or self-terminating, and solutions that say civilizations are out there, but we are failing to detect them for some reason. Let's work through the most important ones. The rare Earth hypothesis says that the conditions required for complex multicellular life are so unusual that Earth-like planets are extraordinarily rare even in a galaxy full of habitable seeming worlds. Perhaps a large moon is required to stabilize a planet's axial tilt, something that requires a specific collision history. Perhaps proximity to a galactic region with low supernova rates is required. Perhaps a specific kind of tectonic activity is needed for the carbon cycle that regulates climate. Perhaps the transition from prokaryotic to eukaryotic life requires such improbable chemistry that it has essentially happened once in the history of the universe. All of these are plausible. None of them have been definitively refuted, but none of them have been confirmed either, and as we discover more about extremophile life on Earth, and learn more about the diversity of potentially habitable environments in the solar system and beyond, the rare Earth argument becomes harder to maintain with confidence. The transcension hypothesis suggests that advanced civilizations do not expand outward into the galaxy. Instead, they expand inward, into miniaturization, into virtual reality, into increasing density of computation in ever smaller physical volumes. A civilization that has mastered nanotechnology and mind uploading might find an expanding virtual universe inside a grain of matter more interesting and rewarding than the cold vacuum of interstellar space. This is genuinely interesting, as a hypothesis, because it is not falsifiable in any simple way. We can't easily prove or disprove that civilizations are all living in tiny, ultra-dense computing substrates, but it has problems with time. Even if civilizations predominantly go inward, we should still expect to see some fraction of them, even a small fraction, that expand outward. And over billions of years, even a rare outlier that chose expansion would have had time to be everywhere by now. The zoo hypothesis and its relatives, sometimes called the planetarium hypothesis, the dark forest theory, or various other names, suggest that other civilizations are out there and are aware of us, but are deliberately avoiding contact. They are watching us develop. They are quarantining us for our protection or for theirs. They are running a simulation. They are maintaining a policy of strict non-interference. These hypotheses share a critical weakness that is almost never discussed with sufficient force. They all require perfect coordination across every single civilization in the galaxy, sustained for billions of years, with no defectors. The zoo hypothesis does not merely require that one or a few civilizations choose not to contact us. It requires that every single civilization that has ever reached the capability to contact us, across potentially billions of years of cosmic history, has chosen not to, with no exceptions, no rogue actors, no civilization that decided the policy was wrong, no signals accidentally leaked, no artifact accidentally left within our range of detection. The probability of that kind of universal, sustained coordination approaches zero as the number of potential civilizations increases and as the time period stretches. The self-destruction hypothesis, broadly equivalent to the filter-ahead interpretation we discussed, says civilizations tend to destroy themselves or collapse before they can make a significant mark on the universe. This is the hypothesis that is hardest to dismiss, and it is, of course, the most uncomfortable one. We will return to it. The simulation hypothesis deserves a brief mention because it surfaces in every Fermi Paradox discussion. If we are living in a simulation, the absence of aliens is easily explained. The simulation doesn't include any, or restricts our observable universe to prevent us from encountering them. This is technically an explanation for the silence, but it is not a scientific one in any useful sense, since it is essentially unfalsifiable and can explain any observation whatsoever by adjusting the parameters of the hypothetical simulation. None of these solutions, standing alone, is entirely satisfying. Each of them leaves loose ends, and most of those loose ends become significantly worse when you factor in the temporal dimension. Chapter 4. Adding Time. Why the universe's age makes everything worse. Here we arrive at the part of the Fermi Paradox that most popular treatments either skip over or underemphasize to the point of distortion. Here we arrive at the temporal dimension, at what happens when you stop asking, why aren't there any aliens here now? And start asking, why hasn't anyone done anything to this galaxy in the past 10 billion years? The answer to that question, when you follow it through carefully, is one of the most disturbing things in science, not because it is gruesome or violent, because it implies something about the nature and fate of intelligence in this universe that, if true, has direct implications for us. Let's start with some numbers that are so important, they deserve to be stated clearly and then contemplated, quietly. The Milky Way galaxy is approximately 13 billion years old. The Sun formed approximately 4.6 billion years ago. Sun-like stars, G and K-type stars capable of hosting Earth-like planets in stable habitable zones for billions of years, have been forming in the Milky Way for at least 8 to 10 billion years. That means there are stars in our galaxy that are 8 billion years old, around which Earth-like planets could have formed 8 billion years ago, on which the kind of chemistry that produced life on Earth could have started running 8 billion years ago. Our civilization, measured from the beginning of agriculture, is roughly 10,000 years old. Our industrial civilization is about 300 years old. Our space age is about 70 years old, now. Imagine a civilization that formed on one of those 8 billion-year-old star systems. Imagine that civilization followed a trajectory even broadly similar to ours, that it took roughly the same amount of time to go from single-celled life to technological civilization. Then that civilization reached our current technological level approximately 4 billion years before Earth formed. It has had 4 billion years of additional development time. What would a civilization do with 4 billion additional years of technological development? There is no good answer to this question because the extrapolation is so far beyond our current capabilities that almost any speculation seems equally plausible. But let us try, starting from conservative physics-respecting assumptions. Our current most advanced spacecraft travel at roughly 0.006% of the speed of light. The Voyager probes, our fastest departing spacecraft, are covering about 17 kilometers per second. At that speed, crossing the Milky Way, which is about 100,000 light-years in diameter, would take roughly 1.7 billion years. That is very slow, but consider, the Wright brothers flew in 1903. 66 years later, humans walked on the moon. The pace of technological development in the 20th century was staggering by any historical standard, and there is no particular reason to think it represented the fastest any intelligence could ever develop. If our pace of technological development continued even roughly, within a few hundred years we could plausibly be building spacecraft capable of a few percent of the speed of light. At 5% of the speed of light, which is within the realm of theoretical possibility using currently understood physics, if exotic propulsion concepts pan out, crossing the galaxy takes 2 million years, a long time by human standards, an eye blink by the standards of a civilization that has been around for 4 billion years. But let's not even use spacecraft. Let's use something simpler, self-replicating probes. The concept of a von Neumann probe, a spacecraft capable of travelling to a new star system, mining materials from local resources, and building copies of itself to send on to the next star system, is well within the bounds of physics as currently understood. No new physics is required, just advanced engineering. If you release a fleet of such probes from your home star system, and each generation takes, say, 1,000 years to reach the next star, mine materials and replicate itself, then the wave of probes expands outward from your home system at roughly 1 star per 1,000 years. The Milky Way, with its 400 billion stars, would be completely explored and physically visited in somewhere between 10 and 100 million years. 10 million years sounds like a lot. In the context of 8 billion years of potential civilization history in this galaxy, it is 0.1% of the available time. If even one civilization launched a von Neumann probe program 4 billion years ago, or 1 billion years ago, or 500 million years ago, every star in the Milky Way should have been visited by those probes multiple times, long ago. Now, extend this further. Even if you don't build self-replicating probes, even if interstellar travel is difficult and expensive, and only a small fraction of civilizations ever attempt it, even if expansion proceeds at a snail's pace of, say, 1 light year per 1,000 years, vastly slower than what physics should allow even with near-current technology, at that glacial rate, crossing the galaxy takes 100 million years, still a small fraction of available cosmic time, still long over by now. The point is not that expansion should be easy or fast. The point is that in a galaxy, billions of years old, even incredibly slow expansion should have finished long ago. The galaxy should have been saturated, physically visited, physically modified, physically occupied, eons before our solar system even formed. And this is not just about colonization or occupation in the aggressive territorial sense. It is about any persistent physical modification of the galaxy at any detectable scale. A civilization that has been developing for 4 billion years and has not expanded might still have built Dyson spheres around its home star, structures that capture a significant fraction of the star's energy output and would be detectable from thousands of light years away through their waste heat infrared signature. We have looked for Dyson spheres. We have surveys specifically designed to find the anomalous infrared signatures they would produce. We have found nothing. A civilization that lived for billions of years and then died would still have left astrophysical traces of its industrial activity, anomalous atmospheric chemistry on its home planet, waste heat signatures from its energy use, possibly structures that persist long after the civilization itself is gone. We have now characterized the atmospheres of dozens of exoplanets with telescopes, and none of them show signatures of industrial activity. Not one, not anywhere. The galaxy looks exactly as it would look if nothing has ever happened in it. And that is the temporal version of the Fermi Paradox. Not, why don't we see anyone right now, but why does the galaxy look like no one has ever existed in it, across billions of years of history? Let's now look at this from a different angle, one that I find even more unsettling than the colonization argument. The argument I just made relies on expansion, on the idea that a civilization would eventually spread beyond its home system, but let's remove that assumption entirely. Let's say civilizations never expand. They never build interstellar probes, or generation ships, or wormholes, or anything that takes them off their home planet or out of their home system. They stay put forever on the planet where they evolved. Even in that case, the temporal Fermi paradox has teeth. Because even a civilization that never leaves its home system would, given billions of years of development, produce signals detectable across the galaxy. Radio leakage, laser communications, the waste heat of industrial or post-industrial civilization, deliberate broadcasts. Any civilization that has been industrially active for even a few thousand years, a tiny sliver of the time available, would have produced a bubble of radio signals expanding outward at the speed of light, detectable by a civilization with our current technology if it passed within a few hundred light years of us. If civilizations are common, and if they typically last for millions or billions of years, the galaxy should be saturated with overlapping radio bubbles. We should not be searching for signals in the noise. We should be drowning in them. Our radio telescopes should be picking up the constant background chatter of a galaxy full of civilizations that have been broadcasting for millions of years. Instead, silence. The temporal Fermi paradox is the observation that the universe has had enough time to be unmistakably full of evidence of intelligent life, not just alive today, but having lived and worked and built and signaled and modified things at any point in the past several billion years, and yet shows no such evidence whatsoever. The silence is not just current. It is historical. It is deep. It extends back through billions of years of cosmic time during which civilizations, if they existed, should have been accumulating artifacts and signals and modifications that would persist long after them. That is what we have to explain, and the explanations, when you take the temporal dimension seriously, become increasingly difficult to find. Chapter 4. Continued. The temporal filter. Time destroys the comfortable answers. Let's now apply the temporal lens to each of the standard Fermi Paradox solutions we surveyed earlier and see what happens to them. The rare Earth hypothesis survives the temporal argument the best of the standard solutions. If complex life is genuinely extremely rare, if Earth is, in some meaningful sense, unique or nearly unique in this galaxy, then the silence is explained without needing to invoke any self-destruct mechanism or conspiracy of silence. The universe is not full of evidence of civilizations because there are no civilizations. There never have been. We are the first, or close to the first, and the universe is vast and old and empty except for us. This is a valid possibility. It is not ruled out by current evidence, but it requires the biological and evolutionary barriers to intelligence to be not just rare, but almost inconceivably rare. Rare enough that in a galaxy with tens of billions of potentially habitable planets, over 10 billion years of time, essentially none of them have produced technology. The probability of intelligence arising per planet per billion years would have to be so small that the expected number of occurrences in the Milky Way across its entire history is less than 1. Less than 1 in a galaxy of 40 billion potentially habitable planets over 10 billion years. That is a profoundly specific and improbable claim about the probability of intelligence. Not impossible, but deeply strange. The transcension hypothesis, civilizations go inward, not outward, also partially survives. If all civilizations, without exception, choose to retreat into miniaturized computing substrates and have no interest in the macroscale universe, then no one would colonize the galaxy, and we would see no megastructures. But the temporal version of the problem remains. Even if a civilization goes inward, the transition involves energy use, waste heat, and astrophysically detectable activity for some period of time, and over billions of years, the accumulated waste heat of even retreating civilizations should be detectable as anomalous infrared signatures in stars throughout the galaxy. We don't see those either. The zoo hypothesis, we are being deliberately avoided, fails hardest under the temporal lens. Not because the hypothesis is obviously wrong in principle, but because it requires the coordination to be both perfect and sustained across billions of years of cosmic time. A policy that began 4 billion years ago and has been maintained without a single exception by every single civilization that has arisen since then is not a hypothesis that should be taken seriously as an explanation for anything. Complex systems, especially systems involving multiple independent actors, do not maintain perfect policy compliance over billions of years. They fragment, they defect, they include members with different values, they break. Even the most disciplined human institutions last centuries at most before fragmenting. A perfectly maintained galactic quarantine across billions of years by potentially thousands of independent civilizations is not an explanation. It is an assumption of something more improbable than the thing being explained. The self-destruction hypothesis, the filter lies ahead, is the one that the temporal dimension does not destroy. In fact, it is the one that the temporal dimension makes more necessary. If civilizations arise and then destroy themselves on timescales short relative to geological time, the galaxy would look exactly as it currently looks, untouched, unmodified, silent, with no trace of past activity. If the typical civilization reaches roughly our current technological level and then collapses or destroys itself within, say, a few thousand years, before it has time to meaningfully modify its star system, before its signals have propagated more than a few thousand light years in any direction, then there might be no detectable trace. The signals would be too faint and too localized. The structures would be too small and too short-lived to leave a lasting astrophysical mark. This is the temporal Fermi Paradox's most important implication. The fact that the galaxy shows no signs of any past civilizational activity anywhere at any point in billions of years of history is most naturally explained by civilizations being either incredibly rare or incredibly short-lived. And given that we have some evidence that life itself is not obviously rare, given what we know about the abundance of organic chemistry in the universe, about the conditions for life on early Earth, about extremophile organisms that suggest life is fairly robust and adaptable, the incredibly short-lived hypothesis deserves to be taken seriously. If civilizations are relatively common but short-lived, the great filter is ahead of us. The thing that kills civilizations comes after they reach technological capability, and the universe's silence across billions of years of history is the accumulated graveyard of those civilizations. A graveyard so complete that even the ruins have dispersed, even the signals have faded below detectability, even the waste heat signatures have redshifted into the cosmic microwave background. That is what the universe looks like. And we are currently at the stage where previous civilizations, if this hypothesis is correct, all encountered whatever it is that ends them. This is where the temporal Fermi Paradox moves from being an abstract astronomical puzzle to being a statement about the human future that should, if you're paying attention, produce a specific and uncomfortable emotion in the general vicinity of your sternum. We will talk about what that statement might mean in the chapters that follow, but first, let us acknowledge something that the temporal dimension reveals about the structure of the problem that is often overlooked. When you think about the Fermi Paradox in purely spatial terms, where is everyone right now? You can maintain some hope that the silence has a benign explanation. Maybe they're out there, just far away. Maybe they're broadcasting on a frequency we haven't checked yet. Maybe interstellar travel is hard enough that no one has reached us. These are all technically possible, and they are all consistent with civilizations being common and surviving for long periods. When you think about the Fermi Paradox in temporal terms, why does 10 billion years of cosmic history show no trace of anyone anywhere? Those benign explanations become much harder to sustain. The silence is not just the silence of the present moment. It is the silence of all the moments that have ever been. It is a silence that extends back through deep time, through the entire history of stars and planets and chemistry and biology, through all the chances and all the opportunities and all the billions of years that have passed since the first potentially habitable worlds formed in this galaxy. That kind of silence is not explained by distance or communication difficulties or the limitations of our current search methods. That kind of silence requires either that intelligence is fantastically rare or that it is fantastically fragile, and the universe, which has shown itself to be extraordinarily good at producing complexity in chemistry and biological information processing, seems like an unlikely candidate for the first explanation, which brings us uncomfortably to the second one. End of Part 1. Part 2 continues with chapters 5 through 8, and the conclusion. The numbers that should terrify you. Let me make the temporal argument even more concrete because I think the abstract version does not fully convey the weight of it. Let's talk about specific numbers and specific timescales and what they mean. The Sun is approximately 4.6 billion years old. It formed from a molecular cloud that had already been seeded with several generations of heavy elements from previous stellar deaths. It is, as far as we can tell, a fairly typical late generation star. There is nothing obviously special about when it formed in the history of the galaxy. Sun-like stars began forming in large numbers perhaps 8 to 10 billion years ago. This means there are star systems in the Milky Way that had sun-like stars and potentially habitable planets forming 3 to 5 billion years before Earth did. If those planets produced technological civilizations, even at the same slow rate that Earth took, roughly 4 billion years from first life to first radio telescope, those civilizations reached our current technological level between 1 billion and 3 billion years ago. 1 billion years, 3 billion years. These numbers are so large they dissolve meaning, so let's shrink them. Suppose a civilization reached our current level 1 billion years ago. In 1 billion years, what can you do if you have access to the energy of a star and the materials of a solar system? What can you do with 1 billion years of scientific and technological progress, building on itself, compounding, the way our own knowledge has compounded just in the last 300 years? What can you do with 1 billion years if even a fraction of it is spent on physical projects in the universe? The honest answer is, we have absolutely no idea. 1 billion years of technological progress is so far beyond our ability to extrapolate that any specific prediction would be fiction rather than science. But we can say one thing with confidence. Whatever that civilization built, whatever it modified, whatever traces it left, they have had 1 billion years to either persist or disperse. And we see nothing. We see nothing on any of the thousands of exoplanet atmospheres we have analysed. We see nothing in any of the infrared sky surveys we have conducted. We see nothing in any of the radio telescope observations accumulated over 60 years of CT. We see nothing in any astrophysical anomaly that current physics cannot explain by appeal to known natural processes. The universe, across 13.8 billion years, looks exactly as it would look if the question "where is everybody?" has only one answer. Nobody has been anywhere. Nobody has done anything. Nobody was ever there. That is the full weight of the temporal Fermi Paradox. Not just the silence of the present sky, but the silence of 10 billion years of cosmic history. The silence of all the civilizations that could have been, and should have been, and apparently were not. The silence of a universe that, by every calculation we can perform, should be full of evidence of intelligent life, and instead presents us with an unmarked, unmodified, pristinely natural galaxy, as though intelligence is either an impossibly rare event or a fundamentally self-extinguishing one. One of those two things is almost certainly true. The question is which one, and the answer, if we can find it, tells us something about what we are and what our future holds. Chapter 5. The Dinosaur Problem: Why Civilizations Almost Certainly Cannot Overlap. There is a thought experiment I want you to do, and I need you to do it seriously rather than skimming past it, because it is the most concentrated version of what the temporal dimension of the Fermi Paradox actually implies. Imagine that intelligent life arises on a planet, let's call it Planet X, somewhere in the Milky Way. The details don't matter much. It is a rocky world, orbiting a sun-like star, with liquid water and a stable climate, and enough time for evolution to do its work. Life originates, diversifies, becomes complex, eventually produces intelligence, and eventually that intelligence becomes technological. Let's say this happens roughly as quickly as it happened on Earth, about 4 billion years from first life to radio telescopes and nuclear weapons. Now suppose this happens on Planet X roughly 500 million years before it happened on Earth, just 500 million years earlier. In the history of a 13 billion-year-old galaxy, 500 million years is not a long time. It is the difference between the Cambrian explosion and today, measured in Earth history. It is a small fraction of the age of the galaxy. It is an entirely unremarkable gap. And yet, a civilization that reached our current level 500 million years ago, and that developed even at a fraction of the pace that our own civilization has developed, if it survived, if it persisted, if it did not destroy itself, would have had 500 million years of additional technological history. Whatever it was 500 million years ago, it is now 500 million years beyond that. And 500 million years beyond where we are right now is not something we can meaningfully imagine. But we can say with confidence that such a civilization, if it exists, has had enough time to do essentially anything to this galaxy that physics permits. It has had enough time to colonize every star system. It has had enough time to dismantle planets and reassemble them. It has had enough time to build structures larger than solar systems. It has had enough time to do things we do not have words for yet, because we have not been around long enough to develop the concepts, and we see nothing. Now let's run the thought experiment the other direction. Suppose intelligent life arises on planet Y, another unremarkable rocky world, 500 million years after Earth. From planet Y's perspective, they are trying to understand why the universe is silent. They have been searching for signals from other civilizations. They haven't found anything obviously artificial. They are 500 million years behind us in development. From their position in time, we are the 500 million year head start civilization, and we are, from their perspective, either undetectable, long dead, or both. This asymmetry is what I call the dinosaur problem, and it is one of the most underappreciated aspects of the temporal Fermi paradox. The dinosaur problem is this: when we ask where is everyone, we implicitly assume that everyone might be at roughly the same developmental stage as us, or somewhat more advanced, or somewhat less advanced. The way neighbouring countries might be at different but comparable levels of technological development. But the universe does not have neighbouring countries. It has civilizations separated not just by space, but by billions of years of time. And in a universe where civilizations could have been arising since at least 8 to 10 billion years ago, any two civilizations that exist are almost certainly not at comparable developmental stages. They're almost certainly separated by millions or billions of years of technological development. Think about what this means. On Earth, 65 million years ago, the most cognitively sophisticated animals were probably dinosaurs or the small mammals hiding from them in burrows. Those animals had no concept of fire, no symbolic language, no capacity for abstract reasoning. They were simply not in the same cognitive universe as modern humans, and there would be no meaningful interaction possible between a velociraptor and a contemporary physicist. The cognitive gap is unbridgeable by any reasonable definition of communication or interaction. Now imagine that gap extended to millions of years, or to hundreds of millions. Any civilization we might encounter in this galaxy, if one exists, has almost certainly been developing for far longer than us, or will develop for far longer than us in the future. The chances that any two technological civilizations in the galaxy are at comparable developmental stages, within, say, a factor of 10 in terms of technological capability, are astronomically small given the billions of years over which civilizations could have been arising. This has a specific and disturbing implication for the Fermi Paradox. It means that the other civilizations we are imagining are not like slightly more advanced versions of humanity. They are either unimaginably more advanced than us, so far beyond us that our very conception of what it means to be a civilization may not apply to them, or they are so far behind us that they haven't produced technology yet, which means they are not the ones who would be making signals detectable to us. The civilizations that should be visible to us, the ones that have had time to spread across the galaxy and modify things and broadcast signals, are not slightly ahead of us. They are billions of years ahead of us, and whatever a civilization does after billions of years of development, whether it is transcendence or collapse or transformation into something unrecognizable, the result is apparently not detectable to a civilization at our current stage. The dinosaur problem also has implications for the zoo hypothesis, and related they are watching us explanations. If the civilizations that would be watching us are billions of years more advanced, then our situation relative to them is not like a primitive tribe being observed by anthropologists from a more developed culture. It is more like a bacterium being observed by a virologist. The cognitive and technological gap is so vast that the relationship between us and them, if they exist, cannot be modelled on any human precedent. We have no framework for imagining what entities billions of years more advanced than us would want, value, care about, or do. This does not mean the zoo hypothesis is impossible. It means it is not a useful explanation, because we have no way to evaluate it. Any behaviour by a civilization billions of years more advanced could be consistent with or inconsistent with a zoo policy, depending on parameters we cannot access. What the dinosaur problem really does is sharpen the central question of the temporal Fermi paradox into its starkest form. If civilizations arise relatively commonly and persist for long periods, then the galaxy is currently populated not by one or a few civilizations, but by hundreds or thousands of civilizations at wildly different developmental stages, ranging from pre-industrial equivalents to things that have been developing for billions of years. In that scenario, the older civilizations have had essentially unlimited time to modify the galaxy in ways that would be visible to anyone. The fact that they have not done so, the fact that the galaxy appears, pristine and unmodified, means either those oldest civilizations do not exist, or they exist and have chosen to leave absolutely no detectable trace of themselves universally across billions of years, with no exceptions. The first option is what the Great Filter implies. The second option is what I would call the Grand Concealment, and I want to spend a moment on it because it comes up in various forms in the literature, and it is worth understanding precisely why it fails. The Grand Concealment says that very advanced civilizations are out there and are simply very good at hiding. They have mastered the art of making themselves undetectable to primitive civilizations like ours. They operate at energy scales or in dimensions or in modes of existence that our current instruments simply cannot register. Their presence in the galaxy is real but systematically invisible to us. Here is the problem. Hiding requires effort. It requires that an entity actively suppress or redirect all the detectable effects of its existence, its energy use, its waste heat, its electromagnetic emissions, its gravitational effects on surrounding matter, its modification of stellar spectra. For a small object in a large volume of space, this might be achievable. For a civilization that has been active for billions of years, and has left physical modifications throughout the galaxy, structures, modified stars, reshaped planetary systems. The effort required to hide all of those modifications retroactively is immense. It is not just a matter of turning off the lights, it is a matter of erasing all evidence that the lights were ever on, across billions of years of activity, perfectly, with no exceptions. And this is before we ask the meta question, why? Why would every advanced civilization in the galaxy invest enormous ongoing effort in concealing their existence from primitive civilizations? The explanations offered: protecting us from knowledge we aren't ready for, maintaining some kind of cosmic quarantine, preventing interference with natural development, all require motives and values that we are projecting onto entities whose nature we cannot even begin to comprehend. And they all require perfect, sustained, universal compliance, which, as we discussed earlier, is the kind of thing that doesn't happen in complex systems with multiple independent actors over billions of years. The grand concealment is not a satisfying explanation. It is a way of preserving the possibility that everything is fine while avoiding the darker implications of the silence. Let us not avoid those implications. Let us go straight into them. Chapter 6. The silence gets louder. What billions of years of absence really means. When you first encounter the Fermi Paradox, the silence feels like a problem of scale. The universe is so big, the distances between stars so vast, that maybe it's not so surprising we haven't detected anyone. Maybe we are just too small and too primitive and too new to notice what is out there. That framing is comfortable. It implies that with better instruments, more time, more sophisticated search methods, we will eventually find the signal we're looking for. It turns the Fermi Paradox from a statement about the absence of civilization into a statement about the limitations of our current technology. The temporal dimension destroys that comfort systematically and thoroughly, because the temporal version of the paradox is not about our inability to detect distant signals. It is about the absence of things that cannot be missed. It is about the physical state of the galaxy, the condition of its stars, its planets, its interstellar medium, its overall structure, and what that state implies about whether anyone has ever modified any part of it. Let's talk about what a long-lived technological civilization would actually do to a galaxy, not speculative far-future technology, just reasonable extrapolations from what we are already doing, extended over millions or billions of years. Energy use is the place to start because it is the most universal and most detectable consequence of technological civilization. All technology requires energy. The more advanced a technology, the more energy it typically requires. On Earth, our total energy use has been growing by roughly 2 to 3% per year for the past 2 centuries. If that growth rate continued for just a few thousand years, not millions, not billions, just thousands, we would require the entire energy output of the Sun. A civilization that has been developing for millions of years would have energy requirements that dwarf the output of a single star. The most efficient way to capture stellar energy is a Dyson sphere, a structure that completely or partially envelops a star and captures its radiated energy. The physicist Freeman Dyson proposed this concept in 1960, not as science fiction but as a serious astrophysical prediction. If technological civilizations exist and persist, they will eventually build structures like this, because the alternative is to leave most of their star's energy radiating uselessly into space. And those structures would be detectable. A star with a Dyson sphere around it would look different from a normal star. Its optical output would be reduced and its infrared output would be increased, as the sphere absorbed the star's light and re-emitted it as waste heat at a lower temperature. This is an unmistakable and distinctive signature. We have looked for this signature. Multiple teams of astronomers, using infrared sky survey data from missions like WISE and 2MASS, have specifically searched for stars with anomalous excess infrared emission, consistent with Dyson sphere construction or partial enclosure. They have found some interesting anomalies, the most famous being Tabby's star, which showed unusual dimming patterns that briefly excited the SETI community. But all anomalies so far have been explained by natural astrophysical processes. No confirmed Dyson spheres, not in the Milky Way, not in the Andromeda Galaxy, not in any of the thousands of galaxies that have been surveyed. Nothing. Consider what this means in temporal terms. There are roughly 200 to 400 billion stars in the Milky Way. If even one civilization per million stars had built Dyson spheres at any point in the past 10 billion years and had not dismantled them, we would expect to see hundreds of thousands of anomalous infrared sources in our galaxy. We see zero. Either Dyson spheres are never built, or they are always dismantled, or the civilizations that would build them don't exist. All three of those options are significant statements about the nature of intelligence in this universe. Beyond Dyson spheres, consider stellar engineering more broadly. A civilization with access to stellar-scale energy over millions of years could modify the physical state of its star, adjusting its temperature, extending its lifespan, changing its composition. The signatures of such modifications would be visible in stellar spectra, anomalous elemental abundances, unusual spectral features, deviations from the normal stellar population in ways that cannot be explained by natural stellar evolution. We have spectroscopic data on millions of stars in the Milky Way. We see no such anomalies. The stars of our galaxy show exactly the distribution of spectra expected from natural stellar evolution. Nothing modified, nothing engineered, nothing touched. Consider planetary surfaces. A civilization that has inhabited a planet for billions of years would have modified its atmosphere in detectable ways. Not just the industrial pollution signatures we look for from carbon dioxide and methane, but deeper, longer-lasting modifications. The chemical composition of a planet's atmosphere is partly set by its biology and partly by its geology. But a technological civilization that has been active for billions of years would have reshaped the atmospheric chemistry of its planet in ways that would not be explainable by natural processes. We have now analysed the atmospheres of dozens of exoplanets using transmission spectroscopy. The results show atmospheres that are entirely consistent with natural chemistry. Hydrogen-dominated gas giant atmospheres, rocky planet atmospheres of nitrogen and carbon dioxide, nothing that requires appeal to technological activity to explain. This is the silence in its temporal depth, not just no signals, no modified stars, no engineered planets, no unusual galaxies, no megastructures, no altered interstellar medium, no evidence at any scale from planetary to galactic that anyone has ever done anything to the physical universe in 13.8 billion years of time. A specific version of this argument that I find particularly compelling involves looking not at our galaxy, but at other galaxies. The Milky Way is relatively young as galaxies go. It began forming perhaps 13 billion years ago, but elliptical galaxies, which are generally older and have been forming stars for longer, should have had even more time for civilizations to arise. If we look at a large elliptical galaxy containing perhaps 1 trillion stars, some of which have been around for 12 to 13 billion years, and if intelligence arises at any reasonable rate, we would expect that galaxy to have been completely restructured by its oldest civilizations long ago. A galaxy that has been inhabited by technological civilizations for 10 billion years should look different from a galaxy that has never been inhabited. The star formation history should be modified. The distribution of heavy elements should show signatures of industrial processing. The infrared output should be anomalous. We observe dozens of large elliptical galaxies in detail. None of them show any sign of civilization-scale modification. They follow the expected laws of natural galactic evolution. They are consistent with being completely empty of technological life, and they have been consistent with that for 13 billion years. The silence is not just current, it is not just local, it is universal, it is historical, and it extends to every scale at which we are capable of looking. And the silence gets louder the more carefully you look. Because every new observation, every new exoplanet atmosphere characterized, every new star spectrum taken, every new infrared survey completed, is another data point confirming the same answer. The universe, at every scale, in every direction, across all observable time, looks exactly as it would look if intelligence has never existed anywhere except here. This is the full darkness of the temporal Fermi Paradox, and it is time to talk about what it might mean. Chapter 7. Dark Solutions. What happened to everyone else? We have now established the problem in its full temporal depth. The universe is old. It is full of potentially habitable worlds. It has had billions of years to produce technological civilizations, and it shows absolutely no evidence of any. not in the present sky, not in the accumulated astrophysical record of billions of years of cosmic history. The silence is not an absence of data. It is data. It is a powerful observation about the nature of intelligent life in this universe. So what are the dark solutions? What actually explains the temporal silence in a way that takes the evidence seriously, rather than explaining it away? There are essentially three categories of explanation that survive the temporal lens with any integrity. I'll call them the rarity solution, the brevity solution, and the transformation solution, and each of them, in its own way, is unsettling. The rarity solution: we are alone, or nearly alone. The cleanest explanation for the temporal silence is that intelligent technological civilization is extraordinarily rare, so rare that in our entire observable universe, it has arisen only once, or only a handful of times, in the most generous estimate, none of which are in our vicinity or even in communication range. This is not a comfortable answer, but it is at least clean. It requires no conspiracy, no universal self-destruction, no transformation into something undetectable. It simply requires that the probability of intelligence arising is so small that in 400 billion stars across 13.8 billion years of history, it has happened essentially once, here, on this planet, around this star, in this quiet corner of the Milky Way. If the rarity solution is correct, then the great filter is behind us. Somewhere in the chain from chemistry to cells to complex life to intelligence, there is a step, or a series of steps, that is so improbable that it essentially never occurs. Perhaps it is the origin of life itself, which we still do not understand mechanistically in any complete way. Perhaps it is the eukaryotic cell, the enormously complex cell type with a nucleus and mitochondria that all complex life on Earth is built from, a cell that appears to have arisen only once in Earth's history through an extraordinarily improbable endosymbiotic merger between two very different organisms. Perhaps it is the evolution of something like the human brain, the specific combination of social intelligence, symbolic language, abstract reasoning, and manual dexterity that enabled the cultural accumulation that eventually produced technology. Any of these could be the filter, or some combination of all of them. If the rarity solution is correct, then the universe is mostly empty of intelligence by design. Not divine design, but probabilistic design. Intelligence is an unlikely outcome of chemistry, and we are a statistical outlier. The emotional weight of the rarity solution is a particular kind of loneliness. Not the loneliness of being ignored or quarantined or watched from a distance. The loneliness of being genuinely, possibly cosmically alone. The loneliness of looking out at 400 billion stars in our galaxy and 2 trillion galaxies in the observable universe, and knowing, or at least strongly suspecting, that in all of that vastness and age and complexity, we might be the only ones asking the question. There is a version of this that I find particularly poignant and disturbing in equal measure. If the rarity solution is correct, then this moment, this civilization, this era, these conversations may represent the only time in the history of the universe that the universe has looked at itself through eyes capable of asking what it is. We may be the universe's single attempt at self-knowledge, and if we are, then what we do with this civilization, and whether we survive and persist or destroy ourselves, is not just important to us. It is, in a strange and vertiginous sense, important to the universe's record of having understood itself. The brevity solution. Intelligence is fragile and short-lived. The second major solution, and the one that has the most direct and uncomfortable implications for us specifically, is that intelligence arises at a reasonable rate but destroys itself quickly. Civilizations appear, develop technology, reach a critical threshold of destructive capability, and collapse before they have time to leave any lasting mark on the galaxy. The average lifespan of a technological civilization is short, perhaps a few thousand years, perhaps less, and so the galaxy at any given moment contains very few active civilizations, and the accumulated evidence of past civilizations is too faint and too brief to detect. This is the forward filter hypothesis. The great filter is not behind us in biological history. It is ahead of us, in the near future, in the form of some technology or some tendency or some dynamic that civilizations at our level of development almost universally encounter and almost universally fail to survive. The brevity solution explains the temporal silence beautifully. If civilizations typically last only a few thousand years after reaching technological capability, they do not have time to build Dyson spheres or send self-replicating probes to other stars or meaningfully modify their stellar environments. Their radio signals propagate outward as an expanding shell that is only a few thousand light-years thick and only a few thousand years old, narrow, faint, and sparse enough that the probability of it overlapping with another civilization's listening window at the right time and right frequency is very small. When the civilization ends, the signals fade below background noise within geological time, the evidence disperses, the universe reseals itself as though nothing happened. The brevity solution is what makes the Fermi Paradox genuinely personal, because if the typical lifespan of a technological civilization is short, and if we are a typical technological civilization, then we are probably approaching whatever it is that ends them. We are not at a random point in civilizational history, by anthropic reasoning, by the simple fact that we exist right now to observe our own situation. We are almost certainly somewhere in the middle portion of our civilization's lifespan. If civilizations typically last 10,000 years, we are probably within a few thousand years of the end. If they typically last 1,000 years, we may be within centuries. What kills them? The candidates are not hard to identify, and most of them are already familiar to anyone who reads the news. Nuclear weapons, which we have had for 80 years, and which represent, even in the current geopolitically fractious world, an ongoing existential risk. Engineered pathogens, which the intersection of advancing biotechnology and malicious actors brings progressively closer to feasibility. Climate destabilization, which is already underway at a pace that has no historical precedent in the geological record. Resource exhaustion and ecosystem collapse, which proceed on slower timescales but with significant civilizational consequences. And perhaps most uncertainly, artificial intelligence, the development of systems that either directly pursue goals misaligned with human survival or indirectly enable the kind of information warfare and social fragmentation that prevents collective action on any of the other threats. The disturbing thing about this list is not that any one item on it is obviously destined to end civilization. It is that we have multiple independent catastrophic risks developing simultaneously, each requiring global coordination and sustained political will to manage, at a moment in history when global coordination and sustained political will are in demonstrably short supply. And we are a very young civilization with a very short track record of managing anything of this kind successfully. The brevity solution says that every civilization that reached our stage of development eventually encountered this same constellation of problems, this same moment where the capabilities of the technology outrun the maturity of the institutions and the wisdom of the actors wielding it, and most of them failed to get through it, not because they were stupid or evil, because the problems are genuinely hard, and the window for solving them is genuinely narrow, and the universe does not grade on a curve. The transformation solution: intelligence transcends detectability. The third major surviving solution is the most philosophically interesting and the hardest to evaluate. It says that long-lived civilizations do exist, but that they undergo transformations that make them invisible to observers at our developmental stage, not through deliberate concealment, but as a natural consequence of what they become. The transcension hypothesis, which we touched on earlier, is the most developed version of this idea. Advanced civilizations, the argument goes, do not expand outward into the cold vacuum of interstellar space, because outward expansion is not where the interesting action is. The computational density, the energy efficiency, and the information richness per unit volume of space all favor miniaturization over expansion. A civilization that has mastered quantum computing, nanotechnology, and the physics of information processing might find more subjective experience, more meaningful existence, more computational richness in a cubic centimeter of engineered matter than in a billion light-years of conventional space. They go small, not big. They colonize the interior of matter, not the exterior of galaxies. If this is true, then advanced civilizations are not absent from the galaxy. They are everywhere, but they are invisible to us because they have compressed themselves below any scale we can observe. They exist in objects that look like unremarkable dense matter. They process unimaginable quantities of information in volumes that our instruments register as physically featureless. This is a genuinely interesting hypothesis, It is not falsifiable in any obvious way, which is both its strength and its weakness as a scientific proposition. It is also not complete. Even if most civilizations go inward, some should go outward, either by choice or by colonization of their miniaturized selves to new locations. And a civilization that has been running for billions of years in miniaturized form would have accumulated enough computational substrate that even a tiny fraction, devoted to macro-scale activity, would be enormously detectable. But the transformation solution gestures at something important, that the silence might not be an absence of intelligence, but a failure of imagination on our part. We are searching for civilizations that look roughly like us, scaled up. We are searching for civilizations that want what we want, that value what we value, that organize themselves in ways we can recognize. And perhaps the most common outcome of long technological development is something so far from our model of civilization that our entire search methodology is like trying to detect a city by looking for mammoth bones. This is uncomfortable in a different way from the rarity solution or the brevity solution. It is not immediately threatening to our survival, but it does suggest that the universe may be full of something, perhaps full of mind in some form, that we are completely unable to recognize as mind, and that the cosmic silence we perceive might be the silence of a dog in a library, surrounded by an incomprehensible richness of meaning, with absolutely no tools to access any of it. Chapter 8. The Last Intelligence. What all of this might mean for us. We have been building toward this chapter for the entire video. Everything we have covered, the Fermi Paradox, the Drake equation, the Great Filter, the temporal dimension, the dinosaur problem, the full depth of the historical silence, the three surviving solutions, all of it converges on a question that is ultimately not about astronomy. It is about us. It is about what this civilization is, where it sits in the story of the universe, and what it might do with that understanding. Let me start with what I think is the most honest assessment of where the evidence currently points. The temporal Fermi Paradox, taken seriously, and without the softening that most popular treatments apply to it, suggests that the silence of the universe is not an observational artifact. It is a real and deep fact about the nature of intelligent life. The universe has had time to be full of evidence of civilization, and it is not full of such evidence. That means either civilizations are very rare, or they are very short-lived, or they undergo some transformation that makes them undetectable. Of these three options, the one with the most direct and actionable implications for us is the second one, that civilizations are fragile and tend to destroy themselves shortly after reaching technological capability. If that is true, if the temporal silence is the accumulated graveyard of civilizations that destroyed themselves at roughly our current stage of development, then we're not just living through an interesting period in history. We are living through the period that almost always ends badly. We are living in what might be called the critical window, the brief interval between the development of technology capable of civilizational destruction and the establishment of the institutions, values, and governance structures capable of managing that technology safely over generational timescales. That window, if the brevity solution is correct, is narrow, not in the sense that we have only days or years, but narrow in the sense that civilizations at our stage typically do not survive for thousands of years into the space age. They encounter the filter first, whatever the filter is: nuclear war, engineered biology, misaligned artificial intelligence, resource collapse, or some combination. It typically arrives before the civilization has had time to become genuinely multi-planetary, genuinely long-lived, genuinely robust against single-point failures. We are right now in that window. I want to be careful here, because the temporal Fermi Paradox is not a prophecy. It is a prior probability. It is a statement about what has apparently happened to most civilizations based on the observed silence of the universe. It is not a statement about what must happen to us. Civilizations do not share a deterministic fate. Probabilities can be beaten. Rare outcomes occur. The fact that most civilizations appear to have failed does not mean we are required to fail. But it does mean that the default outcome, the outcome we get if we do nothing different, if we continue on our current trajectory without seriously addressing the existential risks that are accumulating, is apparently bad. Apparently very bad. The universe is telling us something, with its silence, about what happens to civilizations that do not solve the problems we are currently failing to solve. What are those problems? I have already named them, but I want to be specific. because vagueness is the enemy of urgency. Nuclear weapons. There are approximately 12,000 nuclear warheads in existence distributed among 9 nations. The arms control architecture that limited and constrained nuclear arsenals during and after the Cold War has largely collapsed. New technologies, hypersonic missiles, autonomous weapons systems, submarine-launched systems with minimal warning time, are shortening the decision windows available to leaders in crisis situations. The probability of nuclear war in any given decade is not high, but it is not zero, and civilizations do not get to survive existential risks that are merely not zero over long timescales. Engineered biology, the biotechnology revolution is producing year by year increasing capability to design and synthesize biological agents. The same tools that enable breakthrough medical treatments also enable, in principle, the creation of pathogens with tailored transmissibility, lethality, and immune evasion. The bottlenecks that currently prevent this from being done by small groups or individuals are primarily technical, and those technical bottlenecks are eroding. The governance frameworks for managing this risk are embryonic at best. Artificial intelligence. This is the newest member of the existential risk list and perhaps the most uncertain. The question of whether advanced AI systems will be aligned with human values and interests, whether they can be built in a way that makes their goals reliably compatible with human survival and flourishing, is currently unresolved. The systems being built are becoming more capable faster than the understanding of their internal processes is advancing. We are building things we do not fully understand at an accelerating pace, with enormous economic and strategic incentives to move faster than is safe. Climate change. This is the most visible and most politically contested of the existential risks, but it deserves to be named plainly. The current trajectory of greenhouse gas emissions is consistent with warming levels that would cause catastrophic disruption to agricultural systems, coastal infrastructure, and political stability in ways that the current international order is not obviously capable of managing. Climate change does not directly threaten human extinction. Humans are remarkably adaptable, but it threatens the stability and continuity of the civilization that produces the institutions and technologies needed to manage the other risks. These are not science fiction scenarios. They are the current operational landscape of a civilization at our stage of development, and the temporal Fermi Paradox says, with the quiet authority of 10 billion years of cosmic silence, that civilizations at this stage usually don't make it. But here is what I find genuinely interesting, and what I want to end on before the conclusion. The temporal Fermi Paradox is not just a reason for despair, it is a reason for a very specific kind of urgency, because if the silence is caused by civilizations failing at the critical window, and if we are in the critical window, then we are not in a situation where the outcome is predetermined. We are in a situation where the outcome is being determined right now, by the choices that this generation and the next few generations make. The filter is not a force of nature that acts on civilizations like gravity acts on objects. It is the aggregate consequence of decisions made by intelligent agents, by people, by institutions, by governments, about how to manage the technologies they have created, which means it can, in principle, be avoided. Not easily, not automatically, not without the kind of collective effort and sustained attention that our current political and social systems are not well designed to produce. But the possibility exists, and it exists precisely because we have the ability to see it coming. We can read the silence, we can understand what it implies, we can look at the universe and see, in its absence of evidence for other civilizations, a warning that is addressed specifically to us. Most species that have ever lived on Earth had no ability to understand the risks that ultimately ended them. The non-avian dinosaurs, who dominated this planet for 165 million years, had no capacity to prepare for the asteroid. They were large, successful, and utterly at the mercy of a universe they could not comprehend. They left no record of their understanding. They could not. We can. We have the extraordinary and possibly unique capability, or at least the unusual capability, to understand the risks facing our civilization, to model them, to study them, to design interventions, and to make choices. That capability is itself a kind of grace, an unearned advantage in the lottery of species. Whether we use it wisely enough and quickly enough is not written in the stars. It is written in what we do next. The universe has been silent for 10 billion years. The silence is a message, The question is whether we are listening. Conclusion. Let's come back down to Earth. We started this video with a simple question. Where is everybody? 4 words. The Fermi Paradox. We built from there through the Drake equation and the Great Filter and the full menu of proposed solutions. And then we did the thing that most Fermi Paradox discussions avoid. We added time. We asked not just, why don't we see anyone right now? But, why does 10 billion years of cosmic history show no trace of anyone, anywhere, ever? The answer to that deeper question is harder and darker. It does not yield to comfortable explanations about communication difficulties or search limitations or the vast distances between stars. It yields only to one of 3 conclusions: that intelligence is extraordinarily rare, so rare it has essentially happened once, or that intelligence is extraordinarily fragile, so fragile that it almost always destroys itself before leaving a lasting mark on the universe, or that intelligence transforms into something undetectable, retreating from the macro-scale universe in ways that make it invisible to observers at our stage. None of these conclusions are comfortable. The first one tells us we may be alone in the universe, which is a loneliness so vast it is difficult to even conceptualize. The second one tells us we are probably approaching whatever it is that ends civilizations, which is the kind of information that should produce both urgency and action. The third tells us the universe may be full of mind that we cannot recognize, which is philosophically disorienting in ways that don't obviously resolve. What the temporal Fermi paradox does, at its best, is shift the question from an astronomical puzzle to a civilizational mirror. It takes the silence of the sky and reflects it back at us as a statement about ourselves, about what we are, about how fragile we might be, about what it would mean to be one of the rare civilizations that makes it, that passes through the critical window, solves the unsolved problems, establishes the institutions and values needed to manage its own technologies, and persists long enough to leave a mark on the galaxy that could not be missed. It would mean being the civilization that breaks the silence. The first civilization in the history of this galaxy, as far as we can tell, to survive long enough to become genuinely detectable, genuinely persistent, genuinely present in the universe as a lasting and unmistakable fact. The first civilization to answer the Fermi paradox from the inside by becoming the answer. Every technological civilization that has ever existed, if there have been others, probably sat exactly where we sit now, looking up at a silent universe, running the same calculations, arriving at the same conclusions, facing the same choice. Either the next chapter of this civilization writes a new kind of story in the galaxy, or it becomes another entry in the long census of civilizations that almost made it. The universe has been watching this planet for 4.6 billion years. For 4 billion of those years it was watching chemistry. For a few 100 million years it was watching biology. For a few million years it has been watching intelligence. And for the past 10,000 years, an eye blink, it has been watching something that is capable of understanding what it is watching. We are the universe looking at itself. We are the question the universe has been trying to ask for 13.8 billion years, finally finding a mouth to speak with. Whether we also become the answer, whether we become the proof that intelligence can survive its own technologies and persist long enough to matter, is the most important open question in the history of this planet. The sky is silent. The silence is a challenge, and it is addressed to us. Thanks for watching.